Thank you to Brilliant for their generous support of SciNexX. While it is important to note that neutron stars aren't classified as dark matter, intriguing recent research indicates that these stellar remnants may actually generate substantial amounts of dark matter. This process could also lead to the production of axions, which are considered key candidates in the ongoing search for dark matter. Gaining insights into these fundamental components of the universe is crucial for enhancing our understanding of the standard model of particle physics explains known particles. It encompasses 3 generations of quarks and leptons, plus the bosons that carry the 4 fundamental forces. And don't forget the mass-granting Higgs particle. However, there are a few holes in the standard model. What are its gaps and how do they challenge our understanding? Join us as we explore the future of particle physics. To complete our understanding, we must fill in the gaps. One crucial gap is the strong CP problem. This issue is often considered underrated in physics. It's abstract and challenging to articulate without math. In this video, we attempt to explain it simply. Long story short, the strong force might break certain symmetries. Understanding these complexities is vital for future research. Charge parity symmetry flips charge and does a mirror reflection of particles, like protons or neutrons. In theory, this symmetry should not restore the initial state, but in quantum chromodynamics, QCD, it appears to do just that. To address this issue, a new quantum field is proposed to eliminate CP-violating terms in QCD. Each new quantum field introduces new particles. In this case, the particle is called the axion. Axions are particularly popular in physics since they may help solve important problems. Their properties might provide insights into fundamental questions about the universe. Understanding axions could potentially lead to breakthroughs in our comprehension of dark matter. They're a great dark matter candidate because they're extremely elusive. They interact with the electromagnetic field only very weakly. We discussed the prospects of axionic dark matter in our previous video. However, axions can only be dark matter if they meet specific conditions. So what makes axions significantly interesting to researchers? Their potential to solve long-standing cosmic mysteries. Understanding axions could change our view of the universe entirely. Make up around 80% of the mass of the universe, produced in pretty ridiculous numbers right after the Big Bang. These things may not solve the dark matter problem. We really want to know if they exist. Dark matter is still a vexing mystery. Understanding dark matter could change everything. Join us as we explore this cosmic enigma. We explore the strong CP problem and the role of axions in string theory. Axions are a key prediction in this realm, and understanding the strong CP problem is crucial for broader concepts in string theory. Our team is investigating innovative detection methods for axions, but their elusive nature, due to weak electromagnetic interactions, makes the search challenging yet intriguing. But axions do have an unusual electromagnetic interaction that might give them away in the grand scheme of particle physics. These hypothetical particles, often discussed in the context of dark matter, have a unique property. They sometimes convert into photons, which are the particles of light. This conversion is particularly notable when strong magnetic fields are present, as the interaction becomes more pronounced under such conditions. Conversely, photons can also transform back into axions under the same strong magnetic influences. This intriguing relationship between photons and axions opens up potential avenues for detection and study, making axions a compelling focus for researchers who are aiming to unravel the mysteries of the universe and understand the makeup of dark matter. Scientists are keen to explore these interactions further. This could have a number of effects, like allowing us to shine a light through a solid wall, using magnets to flip photons into axions and back again. Various experiments to detect this phenomenon haven't found anything. That could be because we can't generate magnetic fields strong enough. This could have a number of effects, like allowing us to shine a light through a solid wall, using magnets to flip photons into axions and back again. Various experiments to detect this phenomenon haven't found anything. That could be because we can't generate magnetic fields strong enough. The conversion rate between axions and photons is crucial. More magnetic field strength enhances this conversion. However, the lower limit of required magnetic field strength is unknown. Understanding these limits could lead to detectable signals. Current studies focus on finding that crucial field strength. Detectable signals are essential for future innovations. This research is a gateway to deeper understanding. In modern axion detection experiments, the magnetic fields max out at about 10 Tesla. The current world record magnetic field is 45 Tesla. Not bad for us on Earth. However, this is minuscule compared to the magnetic fields generated by space phenomena. Take magnetars, a type of neutron star with extraordinary magnetic capabilities. These celestial bodies can generate magnetic fields far exceeding anything we can create on Earth. It's a staggering display of nature's power, dwarfing human-made limits. Understanding these cosmic magnetic fields can unlock secrets of the universe. Neutron stars may be efficient axion factories, but that's only true if they meet specific conditions. Let's start with the conditions needed to produce axions. Fields up to the vicinity of 10 billion Tesla are crucial. These conditions are tied to the Big Bang's legacy. Axions connect to the fabric of the cosmos. What can neutron stars tell us about axion physics? Discover how axions are produced in neutron stars. The first key element is a strong magnetic field. Neutron stars are chosen for their magnetic properties. The second element is a source of photons. These photons convert into axions under certain conditions. Understanding this process could unveil secrets of the universe. Join us in exploring the fascinating world of axions. The requirement for axion production is stringent. Axions can be produced when there's a time-varying electric field. This electric field is parallel to a magnetic field. A photon is a single quantum of oscillating electric field. It has a perpendicular magnetic field that travels with it. Sending photons into a magnetic field can yield fascinating results. Sometimes the electric field of photons aligns with the external magnetic field. This alignment can lead to the production of axions, fascinating particles in physics. To generate a substantial number of axions, we need a multitude of photons. The relationship between photons and axions is a crucial element of modern physics. Understanding these interactions can unlock new dimensions in our understanding of the universe. Join us as we delve deeper into the world of quantum particles. The most promising way with neutron stars is a large-scale electric field. Neutron stars generate strong electric fields due to rotation. These fields are stronger than individual photons. Early neutron star models suggest this phenomenon. Understanding the interaction of magnetic and electric fields. Exploring the dynamics of neutron star environments. This research opens new doors in astrophysics. This is related to the effect in a standard electrical generator, where rotation of conducting material in a magnetic field generates current. In a neutron star, a component of the electric field is generated. This electric field should be in the direction of the magnetic field. Now we'll come back to the requirement. Let's explore the dynamics of electric fields. Nature resists parallel electric and magnetic fields. This phenomenon helps to explain axion production. The behavior of these fields is crucial to physics. Nature's complex relationship with these forces is fascinating. Understanding these principles can unlock new discoveries. Join us as we delve deeper into these interactions. And it does this in a couple of ways. First, this electric field generated tends to rip charges from the neutron star. The changes rearrange themselves to neutralize the parallel component of the electric field. Secondly, when the strength of the electric field gets high enough, we expect a phenomenon similar to lightning. Under extreme voltages, insulating materials can become conductors. This process is known as electrical breakdown. When charge builds up, electrical breakdown occurs in the air. This results in the flow of massive currents, aka lightning. Well, let's dive deeper into this natural phenomenon. Join us as we unveil the mysteries behind lightning. The vacuum is a pretty good insulator, but it can also break down under extreme voltages. The result of this vacuum breakdown is the production of electron-positron pairs. In a neutron star, this process has significant implications. These pairs of particles work to short out the electric field. Understanding these interactions helps us learn about fundamental physics. Join us in exploring the mysteries of the universe. Could nature shut down axion production? Neutron stars are extreme environments. The region around neutron stars creates a magnetosphere. These magnetic fields are among the strongest in the universe. Neutron stars defy our understanding of physics. What secrets do neutron stars hold? The mystery of the universe continues to unfold. The super-intense magnetic field co-rotates with the star. In some cases, it spins up to several hundred times per second. The further we get from the neutron star, the faster the magnetic field lines sweep through space. This keeps up with the rapidly spinning surface of the star. Magnetic field lines lag behind the surface. They don't move faster than light. This creates a helical pattern in the magnetosphere. Field lines are essential to understanding magnetism. Exploring the interactions of magnetic fields. These principles apply to planets and stars alike. The study of magnetism is a vital aspect of physics. Fields trailing off into space arise from neutron stars. These fields twist and induce flowing currents, as per Ampere's law. Charged particles are lifted from the magnetosphere at the polar cap region. They travel along helical field lines into the vastness of space. These particles are then sprayed into space, adding to cosmic phenomena. The interaction of magnetic fields and particles is a critical aspect of astrophysics. Understanding these processes helps unveil mysteries of the universe. Fields trailing off into space reveal secrets. These fields arise from regions around the neutron star's magnetic poles. The twisting magnetic fields induce currents according to Ampere's law. Charged particles are lifted from the magnetosphere. They travel along helical field lines into space. These charged particles are sprayed into space. A captivating display of nature's forces in action. Now remember that an excess of charged particles can shut down our electric field. These particles can come from the surface or through vacuum breakdown. We now have a way to drain those particles into space. This means we can maintain stability in our electric fields. Understanding these processes is essential for advancements in space technology. We may be able to rescue our axion factory. So do we get axions or don't we? Bringing together everything I described, we end up with a hellishly complex process. That is very difficult to fully explore. With just pen and paper, the only way to properly analyze this is through advanced methods. In our quest to understand neutron stars, we use simulations. These are based on plasma particle and cell simulations. Nature seems not to hinder our axion production efforts. Vacuum breakdown occurs in a bursty manner, An avalanche of pair production shorts the electric field. This phenomenon leads to temporary fluctuations in the field. Then the field switches back to its original state. This leads to precisely what you want for axion production. A rapidly fluctuating electric field creates significant effects. Electric field oscillations emit powerful electromagnetic waves. Neutron stars are known to emit intense radio jets from pulsars. These jets are rich in high-energy particles and waves. We still seek to fully understand these phenomena. The relationship between electric fields and neutron star emissions is key. Exploring the source of cosmic jets, we uncover their mysteries. New simulations may explain these observed radio jets. These simulations may also reveal our axion source. Radio photons and axions take different paths once generated. Radio waves are beamed, aligned with magnetic poles. These jets lead to pulsations observable from Earth. The beam sweeps across our line of sight, creating phenomena. Axions can shoot off in all directions. They can convert back into radio waves. This occurs far from the standard pulsar beam. This leads us to a fascinating prediction. Could this allow us to test for axion production? The quest for understanding these elusive particles continues. Join us as we delve deeper into the mysteries of axions. If axions can lead to radio waves in random directions, we should expect neutron stars to glow across a wide spectrum. However, that isn't the case. Sensitive radio telescopes detect a different reality. Telescopes have been monitoring pulsars for 50 years, but find them largely radio dark. The regular blips of radio beams are all we observe, hinting at deeper mysteries. This darkness aids scientists in setting strong constraints on axions. Observations from 27 nearby neutron stars provide valuable data. Understanding these phenomena could change our view of the universe. Axions produced by neutron stars might not be detectable at first glance, but there's another method to spot them. Around 90% of these axions are expected to escape into space. Some axions are converted into photons on their journey. This conversion can lead to detectable radio waves. Understanding this process could unlock secrets of the universe. Join us in the quest to uncover the nature of axions. Only 10% of the matter is created with velocities below the neutron star's escape velocity. These particles fall back and orbit the neutron star due to their inadequacy to escape its gravity. The escape velocity of a neutron star is incredibly high, around half the speed of light. This means that only the fastest particles manage to escape into space. All others become trapped, caught in the star's strong gravitational pull. Neutron stars are among the densest objects known in the universe, influencing their surroundings significantly. Understanding these dynamics is crucial for astrophysics and our knowledge of cosmic evolution. The captured axions can be traveling fast. These trapped axions build up in a cloud around the star. This cloud builds up over thousands or millions of years. The axion cloud may have observable effects. They might explain a phenomenon called nulling. Nulling occurs when the pulsar's radio emission is suppressed. They might result in bright radio emission too. Yet these emissions are not seen in bright neutron stars. But the radio light from these captured axion clouds has a narrow frequency range. This may have rendered it undetectable in previous searches. When a neutron star's magnetic field fades over millions of years, these axion clouds might evaporate in a burst of radio emission. This radio emission may last millions of years or just a fraction of a second. Models compare mysterious fast radio bursts to potential axion clouds. These bursts, distant and bright, have baffled astronomers. Astronomers seek radio signatures that could uncover the Axion cloud. Radio astronomers are diligently working to pinpoint these gaps. Meanwhile, pulsar experts are refining their modeling techniques. The quest to understand the universe is ongoing and complex. Unlocking these secrets could change our understanding of physics. Let's explore if phenomena like fast radio bursts match observations. Future radio facilities like the Square Kilometre Array may reveal new insights. These facilities may detect axionic radio signatures currently undetectable. Neutron stars may produce axions, but not enough to explain all dark matter. We still need a significant amount of axions from the early universe. Understanding these phenomena is crucial for our grasp of dark matter. Continued research may finally unlock the secrets of dark matter. Dark matter factories could help us study axions. Axions may be linked to neutron stars. Are axions one component of dark matter? Neutron stars release countless axions. These particles could be cloaked in clouds. Axions might explain pulsar radio jets. Could axions decode fast radio bursts? That's a lot of ifs, but if these ifs work out, the payoff is huge. It'll be a step beyond the standard model, and perhaps will give us at least one of the components of dark matter. Definitely worth keeping our eye on these neutron stars to see what strange things are being formed in those tiny patches of curved spacetime. Thank you to SciNexX for supporting this channel. SciNexX is where you learn by doing, with thousands of interactive lessons. Explore physics, math, programming, and AI with hands-on lessons. Build your critical thinking skills through problem solving. Each lesson is packed with hands-on problem solving. You actually play with the concepts and learn in a fun way. Join SciNexX and take your learning experience to the next level. Don't forget to like, subscribe, and share. Your feedback means a lot to me. Let me know in the comments if you're enjoying videos like this. Your input helps me understand what kind of content you want, so I can keep bringing you fresh, exciting, and informative videos.